Question number 5. Select the correct statement or statements regarding the semiconductor devices. First option A. Electrons and holes are equally density in an intrinsic semiconductor at equilibrium. For this question we will see options one by one. Option A. Electrons and holes are equally density in an intrinsic semiconductor at equilibrium. At equilibrium means thermal equilibrium, means temperature not changing. At thermal equilibrium, temperature not changing. Means temperature is constant. Option A. Temperature is constant. At constant temperature, number of holes and number of electrons are equal. Number of electrons and number of holes are equal. That also equal to the intrinsic carrier concentration. This is option A is correct. This is also we will see in formula way. Actual formula is for thermal equilibrium case, concentration of holes and concentration of electrons formula is there. This is for the concentration of holes at thermal equilibrium. This is for T is equal to constant. At T is equal to constant. He also given in option A at equilibrium means thermal equilibrium, and he also given the semiconductor is pure semiconductor. He is not given any doping levels or any type of semiconductor, just regarding the semiconductor. Then doping are 0, means Na is equal to 0 and Nd is equal to 0. By putting Na is equal to 0 and Na is equal to 0 in both cases, this will gives a P naught is equal to, not means at equilibrium, P naught is equal to root Ni square, that is equal to root Ni square is equal to Ni. Similarly from this also, at Nd is equal to 0, Na is equal to 0, Nd is equal to 0, Na is equal to 0, then it becomes root Ni square, that is equal to Ni. At the thermal equilibrium, number of holes and number of electrons equal to the intrinsic carrier concentration. So option A is correct. Option A is correct. Then option B. Collector region is generally more heavily doped than base region. This is wrong. Collector region is moderately doped, not heavily doped, than base region. Base is lightly doped, but collector is moderately doped, not heavily doped. You will see all the regions of BJT doping levels. Emitter is heavily doped. Base is lightly doped. Collector is moderately doped. In tabular form we will see this. So from this table we will see width. We ignore this width. We need doping concentration. Base is lightly doped. Collector is moderately doped, not heavily doped. Emitter is heavily doped. Not collector. Collector is moderately doped. Base is lightly doped. So our option B is wrong. Option B is wrong. Now we will see the option C. Option C is total current in spatially constant in a two-terminal electronic device in dark under steady state condition. Under steady state condition means there is no application of the external voltage. So without external voltage, there is no current generated within the device. Under steady state, individual currents may vary spatially, but total current But comes to the total current, it is spatially constant. Means in individually electron current or may hole current may vary spatially, but the combination of the total current is for electron and hole total current is spatially constant. Spatially constant. So this statement is correct. Option C is correct. Now comes to the option D. Mobility of electrons always increases with temperature in silicon beyond 300 Kelvin. This is important. Beyond 300 Kelvin. But comes to the mobility versus temperature. This is temperature, this is mobility. Mobility versus temperature. For take this as 300 Kelvin. Before 300 Kelvin means at low temperature, as increasing the temperature, mobility may increase. By reaching this 300 Kelvin means beyond the 300 Kelvin, as increasing the temperature, mobility gets decreases. Gets decreases. This is due to lattice scattering. This is due to impurity scattering. Low temperature is impurity scattering. This is called impurity scattering. Due to impurity scattering, temperature increases, mobility gets increases. This is lattice scattering. Lattice scattering. For high values of temperature, lattice scattering will comes to the picture. So in our option beyond 300 Kelvin, as temperature increases, mobility gets increases, but this is wrong. Mobility of electrons always increases with temperature in silicon beyond 300 Kelvin. This is wrong. Decreases beyond 300 Kelvin, it decreases. So for this question, our answers are A and C are correct. A and C are correct. So remember these formulas. Oneida formulas. If you remember, it's very useful. This is for thermal equilibrium case. This is doping concentrations of base, emitter and collector. We can see here also widths also. This is base width. Let's see this. Width is also. Base is narrow width, emitter is moderately width, collector is wide width. And remember this curve also. For low temperature, impurity scattering. For high temperature, lattice scattering.